All right, so you guys have asked for a couple of practice problems before we get rolling on the new material. And so I want to be sure to provide that for you now. And there's a couple of problems I think that are going to be good to look at. And so let's do this. Let's take a look at a benzene ring connected to a few carbons. Let's have one of the carbons be an isopropyl group. Let's have this one be a chlorine. Let's do another one where we have a cyclohexane with an iodide. And let's have another one where we have a cyclohexane with a bromine and a methyl group. And let's use small bases for all of them. But let's repeat one of them. And let's use a big base. Okay, and so let's think about these four problems and what we're going to do. And so what I want to do is I want to predict both the major and the minor elimination products. And so I've got these four reactions, and for the first three, we're going to use a small base. So remember, when we have a small versus large base, we're thinking about the regioselective outcome of the two elimination products. Remember that the word regioselective means where is the double bond going to form? Regioselectivity is which one of the structural isomers can form. This is as opposed to stereoselectivity, which is which one of the stereo isomers can form. All right, so when it comes to regioselectivity, we don't have to, for the small bases, the major product will always be the more conjugated double bond. When it comes to the larger base, the product that forms in the major quantity is going to be the least substituted of the two alkenes. And so we'll come to that consideration at the bottom for the large base. But for the small base, we want to think about the beta hydrogens and which ones will form the more substituted alkene. So for the first leaving group, we know that the minor product will form from the removal of a hydrogen that will end up being the least substituted. So I want to do the minor product first. That's the one that I did in green. The bond between the chlorine and the green carbon will produce the least substituted alkene. And so this one will be the minor product. Now I want to think about the major product, and the major product in this case will form between the red carbon and the leaving group. But what I want to notice about the position with the red carbon is that there's only one beta hydrogen there. And because there's only one beta hydrogen, we have to do a conformational analysis in order to figure out which one of the which version of, in other words, this is a stereochemical consideration, which stereochemical outcome will be favored. In general, the less sterically hindered of the two possible products will be the predominant product, but because there's only one beta hydrogen, in this case, that means that only one product is actually possible, and we have to think about that. And so I'm going to use the space where I'm going to write the other products to do the analysis, but then I'm going to erase it. So what we remember that we have to do is we have to draw a Newman projection. And so if I were to draw a Newman projection, if I'm going to look at it from this direction, then that means that I have this Newman projection because that bond is pointing down. That means that the chlorine is here, and attached to that, I have a hydrogen there. And this is that methyl group. So let's sort out the rest of this business. And so what do I have going on with the rest of that thing? Well, going up, I've got the phenyl group. So I've got that big benzene going up the bond, starting at the red carbon. Now I have to sort out what's happening with the rest of it. Well, the rest of it, I have this isopropyl group going right, and I've got the hydrogen going left. And so that's not the correct orientation. And as you see, the leaving group is not antiparaplanar to a hydrogen, it's antiparaplanar to the isopropyl group. And so what we have to do is we have to do a rotation. And we have to rotate it this direction so that the hydrogen is in the correct orientation. Now, instead of rewriting the Newman projection, I'm just going to erase things. So I'm going to move everything around one position. And so that means that the phenyl group went here, the hydrogen went here, and the isopropyl went there. And so now that I do have the chlorine antiparaplanar from a hydrogen, I can consider what's going to be on the double bond. So I should draw a double bond, and now I can put the groups together. So on one side of the double bond, I'm going to have a hydrogen, and on the other side, I'm going to have the isopropyl group. Then with the hydrogen, I'm going to have the CH3, and with the CH3, I'm going to have the benzene group. And so this gets me the correct configuration of the major product that's formed. And so this one is major. Any questions about that? All right. So let's take a look at this next one. So it wants us to get the major and the minor product, and I'm going to stick with minor on the left and major on the right for the moment. And so remember that the minor product for the small base will be the Hoffman product. And so in this case, the Hoffman product is the least substituted alkene. So that's going to be the answer for the minor product. The major product will be the more substituted alkene. And so I want to think about either this position or this position because they're both beta hydrogens. But because this is a symmetrical molecule, there's only one possibility. And so the double bond in either location leads to the same molecule. So I only have to write down one answer, and that's the major product there. Okay, and so the next one I have is a bromine and a cyclohexane. The minor product for the cyclohexane, again, with the small base, is going to be the Hoffman product. And the Hoffman product will involve the double bond forming here. And that means that the methyl group has the same stereochemistry and nothing else has changed for that. Now, it's the major product that I have to consider. And the major product starts off here. And so I want to make sure that I can take a look at whether or not that major product will form, because I notice that immediately there is only one hydrogen on the beta carbon. So what I want to do real quick is draw one chair conformation to just sort out in my brain what's going on with these different groups. And so I remember that the only possible way to have a bromine to have a leaving group anti-paraplanar with a beta hydrogen is to have it in an axial position. So I want to go ahead and just start with it in an axial position. And so the other thing attached to that group is a hydrogen. And so when I go around the chain, I've got these two groups here. And so I would need to put the two groups in their appropriate location. And I find that the methyl group is here and the hydrogen is there. And so what I notice then is that the bromine cannot be antiparaplanar to that beta hydrogen to produce what would have been the Zaitsev product. And so at the end of the day, there is no Zaitsev product. The only thing that forms is the one that we labeled as minimum. So in this case, it's not the minor product, it's the only product. All right, and so that leaves us with the last problem with the tertiary butoxide. And remember that the tertiary butoxide is a bulky base. Now, in this case, we have more than one beta hydrogen, so we don't have to worry about doing a conformational analysis. So both of the products will form. When I have a large bulky base, the Hoffman product is the major product, and the Zaitsev product is the minor product. So in this case, I'll just swap the answers around. There's the minor product on the right, or excuse me, on the left, that's the Zaitsev product. The major product on the right, that's the Hoffman product. So that's a couple of examples of how to do some of this E2 predict the product stuff. You know, remember, most of the time I'm just going to ask you for the major product, but you should keep in mind that the minor product is going to be there as well. And so you want to be able to think about which one of those will be the minor product so that you can answer those questions when they pop up. Just pause real quick for one little beat and see if there's any questions in chat. All right, cool. And so now what we want to get onto is the next part of this chapter, which discusses unimolecular reactions. Up until this point, what we've been talking about are bimolecular reactions. And so remember that bimolecular reactions are second order. And so they do involve the rate equations do involve the concentrations of both the substrate and the nucleophile. And the reason that is because remember that the substrate is attacked by the nucleophile at the same time that the leaving group leaves. So the word that we use is concerted. Those SN2 and E2 reactions are concerted. The nucleophilic attack and the loss of the leaving group happens at the same time for an SN2 process. The proton transfer and the loss of the leaving group happens at the same time for the E2 process. Now what we want to look at are unimolecular reactions SN1 and E1. And again, what the one means in this case is that they're unimolecular. That means that the two steps do not happen at the same time. The reason that it's unimolecular, the reason we use that word is that the rate equation is determined based only on the concentration of the substrate. In the case of the substitution reaction, it would not matter how much nucleophile you put into the solution. It's only the concentration of the substrate that determines the rate. And this would be true for the E1 reaction as well. And so what does that mean? It means that these reactions are stepwise. They are both similar in the sense that the first step of the reaction in either case is the same thing. The first step of the reaction in both cases involves the loss of a leaving group and the formation of a cation in the intermediate. It's then what do I do with this cation that determines what happens next. If I have a nucleophile attack, then that would be a substitution reaction. If I do a proton transfer, then that's an elimination reaction and I'll form a double bond. And we'll take these two things independently. And the bottom line with unimolecular reactions is you really have to know and understand what the reagents are and what they're going to do and how that affects the outcome of the reaction. One of the things that I want to mention right at this point is that a lot of times these reactions are actually in competition with each other. And so at some point at the end of this chapter, you want to be able to develop a level of sophistication that allows me to give you a substrate. And then what I would say to you is, and I'm really going to give you a problem like this. I'm going to give you a substrate, and I'm going to say a total of 8 different products, or 5 different products are formed. Figure out every possible product, and then tell me each mechanism that goes to. The question is asked, can you label nucleophilic attack versus electrophile? And I don't think we're there yet. All I was saying with this particular reaction scheme was, if I have a nucleophile here, then that will lead to a substitution reaction. So if the next step of the mechanism is nucleophilic attack, then I will do a substitution mechanism. But if the next step of the mechanism is proton transfer, then it'll lead me to an elimination reaction. And so what we're going to do at this point then is to focus on one or the other. But before we focus on one or the other, I want you to keep in the back of your mind that both of these things are generally in competition with each other. And so you will sometimes have to think about a mix of products. In the textbook for Klein, there's a very helpful chart about how to predict the different products that are formed based on both the substrate and the style of reagent that you have. And so we'll look at that chart and we'll draw it up so that you can kind of get an idea of what that looks like. And I think it's a very powerful chart. It really does help you organize your thoughts. But at this point, what I want to do is I want to draw a line in the sand and specifically talk about an SN1 reaction. So if I do this reaction in, let's say, ethanol, then I can get, then bromine will leave and it'll form an intermediate carbocation. And it's important to remember that a carbocation is formed in the intermediate, because one of the things that we're going to have to deal with these reactions is the possibility of a carbocation rearrangement. And so what will happen in these cases if I have an ethanol or other Protic solvents is that I can get the ethanol to do the nucleophilic attack. This will add an ethanol in that location where the carbocation is. And then eventually, though, in order to form a neutral product, I would have to have something come along and do a proton transfer. And for reasons that I'm not going to mention at the moment, I'm going to show ethanol doing that proton transfer. Even though what I would normally show is that the other product is HCl. Okay. All right. Does anybody have any questions about that particular SN1 reaction? So think about it as being in 2 steps. In this case, it's a minimum of 2 steps. And so I want to make sure that I'm illustrating that in step 1, excuse me, that's not step 1. In step 1, there's the loss of a leaving group. And then in step 2, there's a nucleophilic attack. And in this case, I had a third step where I also had a proton transfer to do to form a neutral product. I can show you an example now. We can do the same type of reaction. We can do it in only 2 steps. And so one of the things is that if I have something like an alcohol, and I react it with sodium bromide, I actually get no reaction. And the reason is that the OH is not a particularly, the question is asked, what does the 1 in SN1 stand for? Again, that's unimolecular. That means that the reaction rate is determined based only on the concentration of the substrate. In other words, it means that the reaction is first order as far as the rate constant is concerned. I'm sorry if that was a little old. So if I react an alcohol with a sodium bromide, I get no reaction because that OH group is not a particularly good leaving group. But I can take this alcohol and react it with an HBr. And in this case, I can get a proton transfer and turn this thing into a good leaving group. And this starts that substitution reaction moving now. I've got the loss of a leaving group. I form an intermediate carbo-cation. And now that bromine that was hanging around, or that bromide that is hanging around, can do the nucleophilic attack. Let me draw that a little less sloppy. And I can add it on. And so there's another, I thought I was going to show you an example where it was only 2 steps, but in this case, it's still 3 steps. I've got 1 step is a proton transfer. 2nd step is loss of the leaving group. 3rd step is nucleophilic attack. And so we'll sort that out here in a second. This is just another example. Let's see if I can I'm trying to do it out of my brain. Let's see if I can come up with an example here. So let's start off with, here's one that'll work out for us. Let's react this with sodium cyanide. So Cn minus is an excellent nucleophile. Again, I can do the loss of the leaving group. I'll form an intermediate carbo-cation. And now the Cn minus can do a nucleophilic attack. And I produce the product there. And so then this is the example I was looking for. 1st step, loss of the leaving group. 2nd step, nucleophilic attack. All right, so eventually there's going to be a lot of different possibilities for this type of reaction. And one of the things we're going to have to do is figure out about all the different nucleophiles that we can use. And so let's take a look at the E1 mechanism in just a little bit more detail. Let's draw a line in the sand and let's think about what E1 has going on for it. If I use the same substrate, but instead of sodium cyanide, I use sodium hydroxide. I get the same 1st step. Remember, because the E1 and SN1 mechanisms have that 1st step in common. So I'm going to use that 1st step to do the loss of a leaving group. But now in this case, I have a base in the solution, and the base could do a proton transfer and I could form an elimination product. Now, if I had replaced this with the same reagent that we showed before, ethanol, then it turns out that ethanol can act as a base as well. So instead of sodium hydroxide, I do the same reaction in ethanol, and now I end up with the same product. And so what I want to illustrate with this switchover of reagents is that before, when I had ethanol in the solution, I showed you a substitution reaction. Now, when I have ethanol in the solution, I'm showing you an elimination reaction. But it's actually the qualities of ethanol that lead to both products. And so this is something that I want you to start to think about, is that depending on the identity of the reagent, you may end up with one product, or you may end up with two products, or you may end up with a big mess of all sorts of possible products. And so it really does matter a lot what this reagent is, you know, as well as what the substrate is, in order to figure out what the product distribution is going to be. Anybody have any questions about that? All right, so the next part that I want to talk about is the possibility for rearrangements in both of these types of reactions. Since the first step of the reaction is the loss of a leaving group, rearrangements can occur. So if I lose this bromine and I form a carbo-cation, and in this case, this is the first time I've shown it, this is a secondary carbo-cation. But we know that there is that secondary carbo-cations are not the most stable, and that we have to think about the possibility of rearrangements when I have carbo-cations that are not necessarily the most stable. In this location, in the carbon right next door to the cation, there is a hydrogen. And let me use my better drawing skills and draw it on the correct side. And that hydrogen can do a hydride shift. And if that hydrogen does a hydride shift, then I end up with a more stable carbo-cation. I now have a tertiary carbo-cation. Now that I have that tertiary carbo-cation, water can act as two different things. Just like before, water can be either a base and do an elimination reaction, or it can be a nucleophile and it can do a substitution reaction. So if water acts as a nucleophile, then water attacks the carbo-cation, and we form this product. But this is also positively charged. And so I will always end up in this particular in Orgo 1 and certainly in Orgo 2 as well, we're always going to be ending up with a neutral product. And so we want to do another proton transfer in order to get that final neutral product, where I have substituted the bromine for an OH group. But keep in mind that the structure is different. The OH group is not at the same location that the bromine was, and that's because of the hydride shift in the intermediate. Because I formed a secondary carbocation, I did a rearrangement, and the rearrangement was a 1,2 hydride shift. Once I did that hydride shift, I had the more stable tertiary carbocation, and that's where the chemistry was going to happen. But also, water can do proton transfers. And so I'm going to use the same substrate. Keep in mind, I'm showing you two separate mechanisms on the same structure. So I'm not saying that both of these things are happening in the same reaction. I'm saying that both of these are possibilities. And so in either case, I form acid as a product. But in one case, I have alkene. And in the other case, I made did I spell alcohol right? No, I'm going to stop embarrassing myself. There we go. And say alcohol group. All right. So again, rearrangements are a possibility. Not only are hydride shifts a possibility, but so are methyl shifts or other alkyl shifts. Any questions about that? Okay. All right, so one of the things that we have to think about in these unimolecular reactions are rearrangements. But just like in SN2 and E2 reactions, I want to think about what are the effects of the different types of solvents. And so when we were talking about SN2, we said that a polar aprotic solvent was something that would favor an SN2 reaction. Well, how does the solvent affect the substitution reactions? And so if I were to think about the different types of solvent, maybe I could have water. Maybe I could have some methanol. Maybe I can have some ethanol. What about acetone? And then this one is diethyl ether. These are very common organic solvents. And so what kind of solvents are they? This one is both polar and protic. This one is both polar and it's also protic. This one is polar and protic. This one is polar and it's aprotic. This one is nice and symmetrical, so it's mostly non-polar. So we would just say it's simply aprotic. If I were to assign a relative reaction rate and assign 1 as the relative reaction rate for ethanol, here's how this works. So the rate increases as the polarity of the solvent increases. Water is definitely the most polar here. If you look at something called the dielectric constant, 78, 30, 33, 24, 21, and 4.3. And roughly speaking, the dielectric constant is a type of measurement of polarity. You see, as the molecule becomes increasingly polar, the reaction rate for any particular rate determining step, which is the loss of the leaving group, speeds up. And so let's think about why that might be. Why might that be? It has some of the same situations going on here. Remember that there's a carbo-cation intermediate that forms. And if I have a carbo-cation intermediate and a loss of a leaving group that will have to be a negative ion, remember that the more polar the solvent is, the better that solvent will be at stabilizing these intermediates. And I'm just sort of drawing some of those interactions to show the stabilizing nature of the polarity of the solvent. And so what does that mean as far as the reaction coordinate goes? If I draw a reaction coordinate for this process, and I think about this particularly polar solvent being able to stabilize the intermediates, and remember that the intermediates are minima, and I use an aprotic solvent. Remember, an aprotic solvent would not have protons like acetone or DMSO, but at the end of the day, I have the same situation going. I can use these solvents to stabilize the chloride because they can interact with the oxygen, but I can't stabilize the positive charge because I'm too hindered to get into there to interact. Hold on, I just said that backwards. I can't stabilize the chlorides. I can stabilize the positive charges because the oxygens can interact with the carbo-cation, but I can't stabilize the chlorides because they're too bulky to get in there and interact with the partially positive sulfurs or the partially positive carbons. I'm sorry, this is a little bit old, but the question was asked, is it a 78 or a 76? It doesn't matter. It was a 78, but it's a lot higher. The point is, it's the most polar. In other words, the oxygen, the partially positive carbon and the partially positive sulfur are too sterically hindered to get in there and do any stabilization for the positive cation. Since the positive cation cannot be as stabilized with the aprotic solvent as it can with a protic solvent, that implies something about the intermediates. It implies that the intermediates are higher in energy in the case of a polar aprotic solvent. What that means is that the transition state leading to that intermediate is higher. And because the transition state with the aprotic solvent is higher, that means that the reaction itself is slower when I use an aprotic solvent than when I use a protic solvent. And so there's one of those things that we're going to have to think about in E1 and in SN1, just like we thought about in SN2. How do we favor an SN2 reaction? Remember that an SN2 reaction has substrate effects and solvent effects. In a second, we're going to talk about the substrate effects for SN1 and E1. Recall that the substrate effects for SN2 was such that an SN2 mechanism prefers a less sterically hindered substrate so that the nucleophile that can readily attack at that less sterically hindered location. In order to promote the SN2 reaction, we said we would use a polar aprotic solvent. And the reason we used a polar aprotic solvent was that it raised the energy of the transition state, or excuse me, it raised the energy of the reactants, thus lowering the activation barrier. A similar kinetic effect is happening here, but instead of raising the energy of the reactants, we're actually lowering the energy of the intermediate. And because we lower the energy of the intermediate compared to an aprotic solvent, we lower the transition state leading to that intermediate. Does anybody have any questions about the solvent and the kinetic effects? I know that you guys love reaction coordinate diagrams as much as I do. I'm trying to keep the chat windows centered so that I can see those questions when they pop up, but it's not always perfect. Okay, cool. All right, so what about substrate effects? With the substrate, you want to think about similar situations to general chemistry acid strength. What were the strongest acids when it came to HBr, HCl, HI, and HF? When we thought, so the question was asked, does an aprotic solvent increase the reaction rate? And so if I know that you can't maybe see it so well over here again, let me draw this again. The aprotic solvent raises the energy of the intermediate. The Hammond postulate tells us that if the energy of the minima is higher, then the maxima leading to that minima is also higher. If we're talking about the same set of reagents, that means we have the same reactants. If we're talking about the same products, we have the same energy for the products. And because those energies are the same, that means that the aprotic solvent increases the activation energy. And if the activation energy is larger, how does that affect the transition state? If the activation energy is, excuse me, how does that affect the rate? If the activation energy is larger, then the rate slows down. Remember, the smaller the hump, the faster the reaction. Hopefully that answers your question there. All right, so back to the substrate. If we think about which one of these halogen-based acids were stronger, if you remember from general chemistry, we would say that only these three were actually considered strong. This one was a weak acid. And the order was 1, 2, 3, from strongest to weakest. And the reason that we said that was the case is that if I have one of these halogens and I'm going to break that bond to make it act like an acid, I'll form these two species. The stronger acid will be the species where X is the most stable anion. And the most stable anion in this case was going to be the iodide anion, simply because iodide was larger, and the word is more polarizable. Because the negative charge is spread out over a larger volume of space, it makes the iodide ion more stable than the other two halogen ions. And that leads to an increase in acid strength. And so when it comes to the substrate and it comes to reactivity towards SN1 and E1 reactions, we get RFs being the least reactive, and RCl, then RBr, and then RI at this direction. So in other words, we're always going to have to deal with an ionization step that is the first step of the unimolecular reaction, the loss of the leaving group. This can be called an ionization. The ionization is more effective when the resulting ion is the most stable, since in all cases this carbocation is the same. It's only the identity of X that matters, and so the larger X is, the faster the rate of ionization is. And so remember that that first step, that is the rate determining step. We know that it's the rate determining step because of the kinetic isotope effect, and kinetic isotope effect is something that I'm not going to do right now live, but it's something I'll follow up with on a video that I'll post online. And so I'll skip over that when I get to that point, but this is how we know that the first step is the rate determining step. The kinetic isotope effect is something that we witness from a experiment that we can do, and that's what leads us to believe that the first step is in fact the rate determining step. All right. So what other kind of cations will form? So what other aspects of the substrate will allow us to form proceed with a unimolecular reaction pretty quickly? Remember that tertiary carbocations are some of the most stable cations. But what about this one? Or what about this one? Will these do SN1 or E1 reactions? If you think about what's going to happen when these things undergo a loss of a leaving group, what kind of products would be formed in that case? These are the benzylic and allylic carbocations. And I'll show you certainly with the allylic cation, remember that it's resonance stabilized, and it's even more stable than a tertiary carbocation. And the same thing is true with the benzylic cation. I'll show you one of the resonance structures. Remember that the charge can delocalize into the ring. And so there's another set of resonance structures. So in both of these cases, when we think about the substrate, of course, the tertiary substrate is going to react very fast. A secondary substrate will also do an E1 or E2 reaction, but it's in high competition with bimolecular reactions. They're often too slow to think about the E1 or SN1 or E1 process happening, but it is in competition with SN2 and E2. A primary substrate cannot form readily a primary carbocation. So this is only, in general, only SN2 or E2 reactions. That's the only case. And so you really do have to think about what's going on with the substrate in order to think about which one of the mechanisms apply. And so one of the things that I haven't really, I mean, I've started to kind of give you an idea of this, but at the end of the day, you have to pick, you have to decide which mechanism is in operation. When you are asked to choose the major product of a reaction, you have to consider what's the substrate? Where is the leaving group located? Is it tertiary? Is it secondary? Is it primary? Or perhaps is it one of these resonance stabilized substrates that would readily form a cation? In that case, you know, you're thinking it's a unimolecular reaction. If it's tertiary or allylic or benzylic, it's easily going to form a cation intermediate. But if it's secondary, it's really kind of a mix of the two. And if it's primary, then you can't form a cation in the intermediate. And so that leads to it leads to a particular set of reactions only. And so I want to just pause a real quick beat there. And I want to see if anybody has any questions about that particular piece. All right, so let's do real quick. Let's just see if we can sort of put that together with some practice. All right, which one of these, in each of these pairs, which ones are more readily able to do unimolecular reactions? In each one of these pairs, which one of them are more readily able to do unimolecular reactions? So in the first pair, the leaving group is the same. So it's not the identity of the leaving group. We didn't specify what the solvent is, and so at this point we don't really have to think about the solvent. And that's going to be the same for the other two examples. So I'm giving you an opportunity to sort of think about it for a second. What is it about, what's the other thing that we need to consider here? The other thing that we need to consider is the substrate. What's the conformation of the substrate? Where is the leaving group located? Which one is it? Is it number 1 or number 2 in the first example? In the first example, in the number 1, the leaving group is located in a primary position. Yeah, in the second one, it's located in a tertiary position. So which one will more quickly undergo unimolecular reactions? Well, the one that's more capable of forming a more stable carbocation. So in this case, it's going to be number 2. Yeah, the tertiary substrate is going to be the fastest. What about in this next example? Which one is going to be faster, 1 or 2? Again, we're not looking at the solvent because that's not specified, and the identity of the leaving group is the same. It looks like they're both in tertiary positions, right? Yeah, but what's going on with this number 2? Number 2 is this position, even though it's tertiary, it's one carbon outside of a benzene ring, and that word is benzylic. It's a benzylic substrate, so it's this one that'll react faster, and the reason is because the resulting carbocation will be resonance stabilized. What about this set? Which one will react faster in a unimolecular reaction? Well, they're both tertiary locations, but what's different is the identity of the leaving group. Which one's larger? Is iodine larger or is chlorine larger? If you remember from General Chemistry 1, iodine is larger, and the larger the resulting anion, the more stable it is. And the reason that it's more stable is because it's more polarizable. It has a larger degree of polarizability. That's the actual vocabulary word. All right, one more example before we move on. Let's actually try to put it all together. Let's do one thing. A mechanism. Well, this will be number 2, and number 1 will be all possible products. So what are the possible products when I react methanol with this substrate and I heat it up? Well, let's think about this. What's the first thing that has to happen in both of these reactions? I've got a bromine at a tertiary position, but it's also benzylic as before. So it will definitely readily form a very stable benzylic carbocation. And now what's next? What are the possible outcomes of this reaction? I've got 2 different pathways that I can go through. I can go through an E1 pathway, or I can go through an SN1 pathway. In both cases, I have methanol as the operating reagent. In both cases, methanol is the thing that's going to do the chemistry. In the elimination pathway, the chemistry that methanol does is act as a base. In the substitution pathway, the chemistry that methanol does is act as a nucleophile. And so let's show it doing both of those things. As a nucleophile, actually I want to go ahead and I'm going to draw it another version of the, because I don't want to crowd my picture this time. In the substitution process, the methanol acts as a nucleophile, and it does a nucleophilic attack. Remember, Me is methyl. When it's acting as a base, it's going to have to do a proton transfer. In the elimination pathway, I'm done. In the second pathway, I am not done. I have to actually do another proton transfer. And so I'll show a molecule of methanol doing the proton transfer and forming the final product. And the final product in this case would be an ether. Or I've formed an ether bond, an ROR bond. Now, if I would have used water, I wouldn't have formed an ether. I would have formed an alcohol. And of course, if I use a reagent that does not function as a base as well as a nucleophile, then the elimination reaction is not possible. There are some reagents that only function as nucleophiles, and we'll talk about those in a second a little bit more, because one of the things you'll have to do is identify those particular types of reagents. All right, so let me stop there, make sure that everybody's got that, see if there's any questions about that. In this case, the heat does lead to both of the products, not just the one. Okay, what about the regioselective outcome when we're thinking about an elimination reaction specifically? What happens when I'm thinking about an elimination reaction from the regioselective possibility? Remember, regioselectivity is which version of the alkene formed. In both cases, I have beta hydrogens. And so that means that I can form a double bond there, or I can form a double bond there. So that means that there's two possible products to consider. There's the product where the double bond forms in this location, and there's the possibility where the double bond forms in that location. Which one's going to be the major product? Of course, what I'm not talking about right now is the other substitution product that's in competition. We're not talking about that right now. We're talking about which one of the elimination products will be the major elimination product. Yeah, it's going to be the one that has the most substituted alkene. Remember, the most substituted alkene is the lowest energy alkene. And so just like before, and I'm showing you only from the intermediate, this is the cation. Actually, let's draw the whole reaction coordinate. I'm not forming a different cation. In this case, this is the cation that I'm forming. Both cations this cation leads to both products. It's all about the next step. Which one of these hydrogens is going to do the proton transfer? And so remember, if we think about the two products, one of them is the least substituted, and one of them is the most substituted. So there is a divergence in the reaction pathway from the position of the cation. So here, this represents the cation intermediate. The Hammond postulate says that the transition state leading to the higher energy product is also higher. So it leads the second pathway, the least substituted pathway, the one that I'll highlight in yellow, with a higher activation barrier. And since it has a higher activation barrier, it's slower. Since it's slower, it forms that product in lesser quantities. It's that same sort of reasoning, the same sort of energetic considerations we've been using as before. The higher the energy of the transition state, the slower that reaction. The slower that reaction, the less of that product is formed. Right? So this is that regioselective consideration. But now what I want to do is I want to consider stereoselectivity. Remember, regioselectivity can only do one thing at a time. Regioselectivity is which one of the possible structural conformations will form. Stereoselectivity is which one of the possible stereoisomers will form. Now, if I think about doing this reaction with water, then I'm gonna have some products. Of course, the product that I don't want to mention right now, or that I'm not thinking about, is the substitution product that's in there. That's not a stereocenter. The ethyl group and the ethyl group are identical, so that's not a stereocenter that's formed. So I don't have to consider stereoselectivity for the substitution product. But what about all the different possible elimination products? Well, let's think about it. I've got one of the elimination products that's already in minor production. I'll call it minor A, because it's the least substituted of the different products. What about the other stereoisomers of the more substituted product? Well, I could have the double bond form with an ethyl group like this. Or I could have it form like this. Which one of these is product? Which one, excuse me, they're all products. Which one of these are the major product? Is it 1 or is it 2? Is it 1 or is it 2? Think about the different stereoisomers that have formed. This is the Z isomer, where the two high priority groups are together. This is the E isomer, where the two high priority groups are apart or opposite. Which one of these is the most favored product, the major product? Did I draw this wrong? I did draw this wrong. Let me back off a second. These two products are the wrong products. I added an extra carbon, so I need to actually redraw it. So let me redraw them really quickly. Essentially the same consideration will apply, but I'll actually have the right number of carbons this time. It's still Z and E. This one is E. This one is Z. Let me make sure I did that right. This one is high, this one is low. Yeah, this one is high, this one is low. Yeah. Now let's think about it. Which one of these two will be the major product? Is it 1 or is it 2? Is it 1 or is it 2? So this is E and this is Z. I'll make sure I did that right one more time. Low, high, high, low. I did. And so let me just say this. It's not necessarily about E and Z. Think about the groups that are interacting. This group is interacting with this group, and this group is interacting with that group. Which two groups would prefer to be interacting? They're going to have an interaction. Yeah, it's definitely a consideration of steric hindrance. Which one is least hindered? Is it the one where the methyl groups are interacting, or the one where the methyl and the ethyl are interacting? It's the one where the two methyl groups are interacting that has the less hindrance. So this is the actual major E1 product, and this is the other minor E1 product. Okay, any questions about that? All right, so moving right along. Now I want to talk about stereoselectivity when it comes to substitution. When we did an E1 reaction, or an SN2 reaction, what happened with the stereo center? We noticed an inversion in the stereochemistry. There was an inversion in the stereochemistry because of the nucleophilic attack happening at the same time as the loss of a leaving group. Remember that the transition state of the reaction oops, draw that wrong. Try that again. That's the bromine that's leaving. I can't draw it that one real fast. But remember that we formed a trigonal bipyramidal transition state. Where the leaving group was leaving at the same time that the nucleophile was attacking. Because this transition state forms the rest of the molecule into a plane, we ended up with an inversion of the stereochemistry. This was backside attack. That's SN2. What about for SN1? What happens if I do a substitution reaction? This is a tertiary substrate with a good nucleophile. This red carbon is a new center, or at least it's a stereo center that forms. This is also a stereo center, but it's unspecified. Now let's go ahead and specify it. Let's go ahead and specify it. Let's specify it. Let's make this a wedge, which means this has to be dashes. Okay. This is unspecified here. What ends up happening? Think about the intermediate. The intermediate that forms is a carbo-cation. What's the geometry of a carbo-cation? So I know that now I really want to stop here just for a second and kind of shake my finger a little bit and think about chapter 1 and chapter 2. Remember that I said in chapter 1 and chapter 2 that this geometry business will come up and be important later on in explaining some of the outcomes of these reactions. Here's one example. What is the geometry of a tertiary, of a carbo-cation? The first thing I want to think about is how many electron groups does it have? 1, 2, 3. That's it, 3 electron groups. So what's the geometry? It's trigonal planar. And so if I were to draw a trigonal planar cation, I'm just going to draw just any version of this. I'm just going to use R groups here. What's going on at that carbon? Remember, if it's trigonal planar and the hybridization is sp2, then that means that there is an unhybridized p orbital. This is that positively charged cation. And I'm not saying that the orbital is charged, but I'm saying that that's where the nucleophile will approach. It can approach from this side, or it can approach from that side. So now, knowing that the nucleophile can approach from either direction, what's the actual stereoisomer that forms? Is it S? Is it R? Or is it both? Well, because the stereoisomer, yeah, it is both, right? Because the nucleophile can attack from either the back side or the front side, I actually get both versions of the stereochemistry that can form. So I get both the S and R configuration. This is called a I want to make sure I'm spelling this right. I'm not finding a good version of it. You'll have to excuse my spelling. I think I'm about to spell this wrong. Racemic mixture. I think it's a C. Racemic mixture, and that means a theoretically 50-50 mix of both enantiomers. Now, yeah, thank you, Shelley. Racemic, R-A-C-E-M-I-C. So it's a 50-50 mix of both enantiomers. In reality, though, it's not quite racemic. In reality, what's going on when we have this carbocation that forms. I do have a cation that forms, but what's happened is that the leaving group is still sort of hanging out. It's not connected to the cation fully, but it's still sort of hanging out. And this is called a proximity effect, okay? And so leaving group is still in close proximity. The word is proximity effect. And so this provides a slight bit of steric hindrance for the retention stereochemistry. So notice that the backside is unhindered. I spelled that terribly. Unhindered. And the front site is slightly hindered. And so that means that we still get a mixture, but the inversion is slightly favored. So even though it's theoretically 50-50, you end up with something slightly different than that. So the inversion, the inverted stereochemistry becomes greater than 50, and the retained stereochemistry becomes less than 50. And it's due to this idea of proximity effect. Right. All right, the next bit is the kinetic isotope effect, but I'm going to skip that and I'm going to do that one all on its own in an offline video. But what I want to do now is I want to start the process of discussing how we predict products. This is going to take more than the 8 minutes that I have left. And so we're going to start here with this same concept and then move into chapter 8 on Thursday. This is a big piece of this chapter though, because at the end of the day, what you're going to have to be able to do is take a particular reactant and a set or a particular reagent and predict all products, and also which one is major and which one is minor. And so you really do have to be able to think about all the different types of products that can form based on the substrate and the reagent. What I want to do is I want to stop sharing here and use this last couple of moments to just give you an illustration of what I mean by that. So just give me 1 second to surf over to my old semesters. And show you this slide. And so this is what I mean by this. at the end of the day, you're going to be faced with the decision. And if you look at the column on the column on the column on the left, that axis is primary, secondary, or tertiary, and determines what's the identity of the leaving group on the substrate. Is the leaving group at a primary position, a secondary position, or a tertiary position? The row at the very top is the identity of the reagent. Is that reagent essentially only a strong base or a very, very, very weak nucleophile? Is it a strong base and a strong nucleophile? Is it a weak base or essentially only a strong nucleophile? Or is it both a weak base and a weak nucleophile? And so this chart sort of helps you predict which of the products will be major. So for instance, if you have a primary substrate and a very strong nucleophile, then the only reaction mechanism that's favored is the SN2 mechanism. If you have a tertiary substrate and a very strong base, then the E2 reaction mechanism is favored because the base is acting as doing a proton transfer faster than the leaving group can leave. But conversely, if you take that same tertiary substrate and you mix it with a weak base or a weak nucleophile like water or ethanol, then you see the same sort of product distribution that we saw earlier. You get a pretty good mix of SN1 and E1. What I want to point out are the X's on this chart. The X's on this chart are not because reactions don't occur. It's because the mix of products is so thoroughly large. You get SN1, E1, SN2, and E2 all mixed together in the same pot that you can't really put it on the chart and have it make sense. And so by and large, on most one-off quick questions that I ask you, I'm not going to put questions that involve this very large mix of problems or large mix of products. But I do want to give you a heads up and let you know that there will be at least one question that you'll encounter at some point that will be essentially one question that gives you one of those substrates, and it puts one of those weak base, weak nucleophile mixes in, and it says, look, predict all of the different products, consider all possible regioselective and stereoselective outcomes. And what that is doing is it's putting together your ability to think about all these different mechanisms, because at the heart of this discussion is these four mechanisms. If you know these four mechanisms, then you can really start to determine what the product distribution will be, but not only what the product distribution will be, what will be the stereoselective and regioselective outcomes. And in order to be able to do that, you have to be able to incorporate the Newman projections and those chair conformations into these mechanisms as you work them through. And so what I'm going to do is I'm going to stop right there. I'm going to stop the recording.